we have seen how in this example of a parent pushing a child on a swing, how we can actually plot a graph of the amplitude of the swings of the swing's oscillation. And this amplitude would depend on the frequency that the parent pushes the child with, and that the swing will swing the most if the parent pushes at the natural frequency of the swing. Right. Let's have a look at this graph and think about what might happen to this graph if there is less resistance in the swing. If you look at the swing, you would expect that as the swing swings, there would be resistance. There could be resistance from friction between the chain and the support. There could be resistance from the air. There could be air resistance. Right. Imagine what would happen. What would happen if these resistance? Now, if I recall the proper term given to this resistance, it is called damping. Damping is the word given to resistance. Damping as in trying to damp down the oscillation, to reduce the oscillation. So if there's less damping, let's think about what would happen to this graph. We would expect that if there is less damping, then at the resonance, that means when the parent pushes at the right frequency, at the right natural frequency, we would expect the amplitude to be that it should be even bigger. Okay, we would expect this to be even bigger if there's less resistance. So we might, for example, get a graph that looks like this. Okay, so this graph is going to look sharper around the natural frequency, or we would also call this the resonance frequency. Right, that's one of the terms that we would learn. The resonance frequency is the frequency at which the amplitude is largest. So the graph would actually look sharper if there is less damping. There's less damping. Now, so in this case, we have seen an example of a good resonance, right? The parent pushing the child. There are many other examples and uses of resonance in everyday life, and there are actually good and bad resonance. Now, let me take a look at some of these examples. Now, if you're watching this on YouTube, right? On YouTube, you could search for videos using the words like voice break glass. Voice break glass. Now, if you search for such videos, you might actually find some demonstrations on how people can use a very high-pitched voice to break a glass. Now, I might imagine, let's say I've just clear this. Let's say I have a glass, maybe a wine glass. Usually, we would use glass which are quite thin. Let's say that's a wine glass. Now let's say there's a person singing with a very high-pitched voice, near the glass. So okay, then there's this person, and the voice from the person travels through the air to the glass and causes the glass to vibrate. How does this glass actually? How can the voice actually cause this glass to break? It's always it always looks amazing when we actually see a demonstration on this, because voice does not seem like a strong force. There might be very loud voice, but a singing voice might not be that strong. And glass is obviously something you hold in your hand, and it's quite hard. So how could this be possible? Let's think about the physics of this. The voice traveling through the air is essentially vibrations in the air molecules. So you have it's actually a pressure wave that travels through the air. So you might imagine that when a person sings or speaks, you have this. The sound generated is basically a region of maybe low and high pressure. So that might be high pressure, low pressure, high pressure, low pressure, high pressure regions that travels outwards. So we would expect that around the glass, when the voice washes over the glass, we would expect that perhaps there would be maybe when the high pressure region reaches this point on the glass, it will push the glass one way, and when the low pressure region comes over here, it might push the glass another way. Okay, so this pressure acting on the glass would cause the glass to maybe change shape. Alright, maybe squeeze the glass just a tiny bit, maybe just by a few atoms at first. Okay, because it's just a very small pressure from the air on the hard material of the glass. So it might just cause it to be squeezed a little bit. Okay, and the high and low pressure region that keeps going past the glass would sort of squeeze and relax on the glass continually. So the glass would get distorted, get squeezed a little bit, and then relax, and then get squeezed a little bit. So that's how it is. All right, that there is this stretching on the glass. Now, but the glass itself has a natural frequency. If you imagine hitting this with, say, your fingernail, or getting a spoon and gently tap at the glass, you will hear a sound, usually a high-pitched sound. Like you hear a sound, and if the singer or the person can make a sound, can sing at the same pitch as that natural frequency of the glass, that voice that continually stretches and pulls at the glass would cause the glass to vibrate. So the glass would move, maybe get compressed, so this way, and then after a fraction of a second it will move the other way. So you keep getting stretched and relaxed, and the amplitude of the vibration can start growing at natural frequency, just like when a parent pushes a child on the swing. And this amplitude can get bigger and bigger. It can get bigger and bigger, and it can get very large actually if there is very little damping, if there's very little resistance. And in the case of a glass, we might think of, say, the hard material of the glass as resisting. But here I'm talking about resistance as in air resistance or other frictional effect that takes away the energy of the motion. But in a glass, this damping, this resistance effect is likely to be very small. So because of this, the vibration would increase and it will get larger and larger, and that's why it's actually possible at the right pitch frequency to cause the glass to break when the vibration gets too big, and it will shatter. So is this a good or bad is this a good or a bad resonance? Well, in this case, it depends on your point of view. If you are trying to drink some water from the glass and it shatters, that's obviously bad. But if you're trying to break the glass for fun or for demonstration, then that would be a good resonance. Okay. Now, in another example, let me look at this example, this famous example of a bridge that collapsed. Let's say these are the two sides of a river or the sea, and these are the two sides. Now, in 1940, in a place called Tacoma in the United States, 1940, to be precise, to be very precise, at 11 a.m. in the morning on November the 7th, something happened to a bridge at Tacoma. Now this bridge looked like this. This bridge, okay, it's quite a long bridge. It's quite a long bridge. And it is supported in this way. There are two pillars, at least, the pillars here, and there are cables. So it's a suspension bridge. This is the usual. This is the common arrangement that we would see. So the cables that suspends the bridge in the air like this. Okay, and there are lots of cars going to and fro on the bridge on the morning of November 7th, 1940. Now on that day, what happened was that there was the usual wind blowing, and the bridge has always been known to oscillate quite a bit in the wind, right? But by as much as some meters. So people are used to it, right? And you can actually find this if you search for Tacoma Bridge on YouTube. You can find some footage of this dramatic event. But on that day, the wind blowing through the bridge somehow starts to cause oscillations in a bridge at a frequency that causes the amplitude of the motion in the bridge to increase and increase. So somehow the wind, by interacting with the structures, by blowing through the bridge, cause the bridge to starts exerting forces on the bridge at the natural frequency of the bridge, right? At the frequency that the bridge would go up and down, and as well as twist left and right. And as a result, the up and down motion and the left and right motion of the increased in amplitude, and it increased more and more. And in the actual footage of the video, what you see is this, what they call this middle span of the bridge. All right, it starts going up and down, and it twists left and it twists right, and motion gets bigger and bigger until in the end the whole of this middle span collapsed and fell to the bottom of the river. Now, so I think we can safely say that this is a bad resonance, because it destroyed the bridge and it almost killed the people who were on the bridge. But luckily, even the last person were able to run off the bridge just in time. Okay, so that's an example of a bad resonance. And maybe just one final example would be let's say we are all familiar with our mobile phones today. And in slightly older days, we have radios. Okay, whether mobile phones or radios, there are antennas, right? Mobile phones and radios have antennas. Now, antennas, and antenna A is a short piece of metal which is inside either the mobile phone or the radio. Now, it is this short piece of metal that would first receive the microwave that comes from the station. All right, that comes from the station that sends out the signal either to the mobile phone or the radio. I just call it the station. So this antenna is normally metallic, and there are electrons inside, right? Tiny charged particles that would start moving when the microwave falls on it. The reason being that the microwaves consist of electric fields that keeps changing direction, that oscillates. So when the microwave from the station that carries your friend's voice signal or your favorite radio station music, when this oscillating microwave or radio wave washes past the electrons in the antenna, the electrons would start moving to and fro in the antenna at the right frequency and in the right pattern, so that the electronics inside your radio or mobile phone can turn it into sound that you can, or music that you can then hear. But in order for this to work properly, in order for the antenna to generate enough current, a big enough current, to so that the electronics can detect this signal, it is important that the electrons that are oscillating in the antenna, it's important that they can oscillate, that the natural frequency of the oscillation of the electrons is the same as the microwave or radio wave frequency. So these electrons in the antenna would oscillate up and down along the antenna, and there would be a natural frequency. Now, this natural frequency actually depends on depends on the length of the antenna. The length of the antenna. So as it turns out, when the length of the antenna is roughly equal to half of the wavelength of this microwave or radio wave in the air, then the natural frequency of the electron oscillating in the antenna would be the same as the frequency from the microwave, and then there would be the biggest current generated in the antenna, and this would then be strong enough for the electronics in the mobile phone or radio to detect the signal and to produce your favorite music or the voice of your friends. So this would be an example of a good resonance. Good resonance.